Well, wonderful. Thank you so much for having me. I just wanted to let you know ahead of time that it is the end of the semester, also known as the most wonderful time of the year. This means that I won't be able to stay too much longer after my talk, unfortunately, but I will leave some contact information if you have any questions about what I present today. So with that, yes, I'm a research assistant professor at the University of New Hampshire. I study mostly snow and climate. I do remote sensing, climate and land modeling, community-based science, K through 12, teacher and student education, and also advocacy and activism. I've been working for a long time with a nonprofit known as Protect Our Winters as a skier and rider for the past 30 years in the New Hampshire area. This is a very important area of research for me, and engaging with local communities on topics such as those are very important. But today we're going to talk more broadly about New England climate and how we can expect to see it change in the future. With that, Rusty had mentioned some releases of very important reports. November 2017, the volume 1 of the Climate Science Special Report, National Climate Assessment, was released. This was the assessment of the physical science, so the broad demonstration of why we're seeing the changes that we're seeing. And volume 2 was released more recently. This was the impacts, risks, and adaptation. So if you haven't checked these out, I strongly recommend it. This one's the one that has been in the news quite a bit lately, and a lot of folks have been working to make sure that the science is being communicated correctly from it. So some of the data you'll be seeing today will be coming from this. As a climate modeler, I'd just like to briefly say what these things are. This is a schematic for a general circulation model or global atmospheric model. It's essentially a series of grid cells that are all connected by physically based equations. They have horizontal grids, vertical grids, and a number of different processes that really at this point aren't that important to go into detail with, but they simulate what's happening in the global system. They've advanced quite a bit from simple radiative transfer models. I do these with my students in my gen ed class. And today they account for biogeochemical cycles and carbon cycling. So they're very advanced in that regard. We've also gotten much finer resolution. Prior models used to be about 500 kilometers, and today most global climate models are simulating on the order of about 110 kilometers. The data I'm going to show you today is from a 4-kilometer statistically downscaled group of models, so it becomes very, very fine resolution. We'll be looking at different emissions scenarios. This is going to be a focus on the future. So what can we expect to see? Well, we have a variety of scenarios that scientists have been using to project into the future. There's the highest scenario, middle scenario, a lower scenario, and then an even lower scenario. And these are the emissions that are associated with that pathway. So currently we're around 10 gigatons of carbon per year. Under a higher scenario, you can expect to see that to almost triple. Under the much lower scenario, we go to 0. Which at this point in time does not seem like a very good possibility, but we'd love to see it happen, because these are the associated temperature responses. Globally, we could expect to see upwards of 8 degrees Fahrenheit warmer temperatures across the world. If you use the lower scenario, then we can limit this to about 2.5 degrees Fahrenheit. So let's go through each little scenario first. The lowest scenario, this is the Paris Agreement version. Okay, this is if countries are working together, we can expect to see a really significant drop in CO2 emissions and carbon emissions in general. Our lower scenario is the one that I'm going to be showing you today. I don't have simulations for our lowest. This is one that is also known as RCP 4.5. That stands for Representative Concentration Pathway. It's essentially just telling you how much CO2 is going to be in the atmosphere. When we look at the details of this scenario, you can expect to see 4.3 degrees Fahrenheit above the 1850 to 1900 average by the end of the century, about 18.5 inches of sea level rise by 2100, and CO2 is going to reach about 650 parts per million. Does anyone know what the current level of CO2 is in the atmosphere? 410, you would definitely get an A+ on my final exam that I'm giving next week. Okay, so this is a number that my students have to remember. 650 is quite a bit higher than that. Anyone happen to know what in the past pre-industrial, before we started emitting CO2 emissions, CO2 was at? You guys didn't know you're getting quizzed this morning, did you? Very close, 280 parts per million. So 650 is a huge change. 410 is already a huge change. Under a higher emission scenario, this is the RCP 8.5, this is also known as our business as usual. Emissions continue, it's very fossil fuel intensive. Now we're looking at 7.7 degrees Fahrenheit above the 1850 to 1900 average. This is globally. 24 inches of sea level rise by 2100, and increasing emissions such that CO2 reaches 1370 parts per million. I cannot emphasize this enough. This is a similar conditions at what we saw when the dinosaurs were roaming the earth. Not to say that the lizards are going to get that large again. However, this means a very warm climate. This means temperate forests growing in Canada where we normally have tundra. Okay? And this is happening very rapidly. In the history of the earth, this has happened before, but it took tens of thousands, even hundreds of thousands of years to go from 600, 400 parts per million to about 1370. Okay, we're doing it in a geologic instant. Where are we now? Well, currently, we just released the 2018 values for carbon emissions across the world from the countries. Unfortunately, we're on track for that higher scenario. We need to start reducing now if we want to reach even this lower yellow, there we go, the lower scenario. Personally, I'd rather be on the Paris Agreement scenario. I think we could all probably agree on that. So let's go in a little bit about the details of the data. This is 16th degree, ends up being about 4-kilometer data for the entire northeastern US domain. We have 29 different models, so it's called an ensemble. That's just fancy speak for our group in terms of like having multiple models. We're not relying on one, we're relying on 29 of them. And by using 29 different models, you have a variety of different ways of approaching the physics in the climate system and also the sensitivity. Some of these models tend to be really sensitive. If you push them with the CO2 forcing, they're gonna have a big temperature response. Other ones are a little bit more weak responses when you give them a CO2 forcing. So we're getting a big range here. This is for the northeastern US. What you're looking at is a single simulation in the thin line. So the gray thin line right over here is one historical simulation. The thicker black line is what we observed. So we can say that the model is doing pretty decently. They're overlapping pretty well. Into the future, we can see this one simulation. This is for a lower emissions, right, the RCP 4.5. We can see that by the end of the century, this particular model is saying somewhere around 16 to 17 degrees Celsius for our average temperature in the Northeast. When we add the rest of the models, so now we're adding 28 more models on top of that, we can see the different range of the models. Let me get that pointer back. I think I'll use this thing. No, that one's not working. Where'd my arrow go? There it is. Okay. Right, so now some of the models, they're showing anywhere between around 13 all the way up to about 17 or so degrees. So this is our range. You can then calculate the mean and say it's about 15.5 degrees, okay? In the higher emission scenario, this is what we're looking at. Okay, so in some cases, we're looking at a temperature that's gonna be around 21 degrees Celsius in the region, and maybe the lower end will be somewhere overlapping with that lower scenario. If you combine the two, you can see that region of overlap, but the average difference between these two ends up being about 3 degrees centigrade. Which may not seem like a lot on a day-to-day variability, but in terms of what our climate system looks like and how our ecosystems respond, this is a huge difference. We had mentioned, or Rusty had mentioned, extreme precipitation. Precipitation. We can also look at extremes in temperature. The Northeast in general, in terms of days above 90 degrees Fahrenheit, we're looking at about less than 5 per year. It's not very common to see the entire Northeast above 90. By early part of the century, the two scenarios are pretty similar, right? Lower emissions and higher emissions. That's the RCP 4.5 and RCP 8.5, but doubling. By mid-century, you start to see them pull away from each other. Now the higher emissions scenario is inching up towards well over 2 weeks. Lower scenario is sticking right around 2 weeks. By the end of the century, we see a doubling, right? So this is the difference between higher emissions and lower emissions for extreme temperature. Now 90 degrees doesn't seem like that much, but this has a huge impact on, say, our electrical grid, right? Not as many people in the Northeast have air conditioning systems as, say, in Florida. What does that mean for the strain on our electrical grid? I'll talk a little bit more about precipitation in a bit and what this means for that. When we think about New Hampshire's summer warming, this is that same sort of graph, right, showing out to the end of the century there, 32 degrees centigrade under higher emissions, maybe 28, so it's about a 4-degree difference. When you think about where New Hampshire is today, well, this is 1960 to 1991, and where it would be at the end of the century, under a higher emission scenario, it's gonna be more like Virginia or North Carolina. Under lower emissions, probably more like DC, Virginia area. Think of the differences between a summer down in DC versus a summer here. Those are the types of impacts we can expect to see as well. I'm a winter researcher, so this one's always my go-to in terms of thinking about what our winter impacts will be, right? So same sort of plot, black is our observations. Note in the past, this is our average daily daytime temperature, so what do we see across the winter? In the region, typically we're below freezing, but there are some winters where things have been above freezing, right? As we move out to the end of the century, under a lower emission scenario, some of the winters, right, of the models are still below freezing for daytime temperatures. But under the higher emission scenario, it is very rare to have a daytime temperature that's averaging throughout the winter below freezing. What does that mean for snow? If you have above freezing daytime temperatures in winter, I think we all know what happens to snow. It's going to melt, right? Oops, there we go. This is what we're looking at historically for snow. Okay, so just walking you, oh, I don't have my legend on there. That's interesting. Okay. So the legend is showing essentially the number of days when the snow depth is at least 6 inches deep. This is, you're putting your boots on, you're shoveling, people are plowing driveways. It's certainly providing an insulative blanket for our soils. And this can be really important for the creatures that live under those blankets of snow, and also the soils and how they retain nutrients throughout the winter. Looking at the graph, sorry, now that we have a legend here, right? Somewhere down in this region, they see about 0 to 20 days per year. As you get up into the northeast, probably 20 to 40 along the seacoast of New Hampshire, same around Newburyport area. As you get into the mountains, certainly inching well up into 180 days per year, right? So they are very snow covered. As we move out to the end of the century, in the lower scenario, much of our region is looking at less than a month of 6 inches or more. Our snowpacks are going to become more ephemeral. They come and go. We've seen that in recent winters, have we not? Right? Winter 2015-16, the winter that wasn't. I was measuring snow up in New England, and we normally get about 90 to 100 days of at least measurable snow, so an inch or more. We had 45 days. It was cut in half. It was exceptionally warm. And this had an impact on the carbon balance in our soils. I'm not going to show you that data. We don't have too much time to go through that. But essentially, forests tend to pulse out a lot of CO2 when you have no snow. Decomposers start getting really hungry. They warm up, and they're chomping away at all the organic material, and they start releasing CO2 to the atmosphere. We'll get to that a little bit in more detail in a bit. Under the higher scenario, again, as a skier and rider, slider, and general recreationist in winter, this is very concerning to me. We're looking at probably chances of having snow-free winters along the New England seacoast, especially right around where we are right now, by 2100. So think about kids and our grandkids. What does that mean when they start reading Frosty the Snowman? Mom, what's snow? Or Grandma? I guess at that point I'd probably be a grandma, right? And you're looking up in the mountains, and we're looking at probably 2 months of snow, which is enough. Right? We can still get out and go hiking. We still have ecosystems that can be supported, but this is going to be a fundamental change in what winter looks like in New England. A lot of my research recently has been focusing, again, not just on snow, but on what's called the vernal window. Vernal, as you might expect, is referring to spring. And this is defined as the period between snowmelt to canopy closure, also known as the shoulder season. It's not quite spring. It's late winter and into early spring. And what we see is that this is a very huge window for ecological opportunity. There's no leaves on the trees, so a lot of sunlight is penetrating the forest floor. We have a lot of snowmelt going on, right? A lot of water moving around and moving nutrients through our ecosystems. We also have a period when a lot of time you're seeing some changes in energy balance as well, because snow is very reflective. We've been looking at this. Groffman et al. In 2012 looked at this in Hubbard Brook, up in northern New Hampshire. This is an experimental forest that's been running for quite some time, since the 1950s. And this is the day of last snowpack. So day 90 would be like end of March, day 120, end of April, and so on. What we can see is that there's been a fundamental change, a decrease, right, in the day of the timing of disappearance of snowpack. That means it's melting out earlier in the year, and on the order of about 2 weeks. So they've lost their snowpack 2 weeks earlier since the 1950s. Recall that that is the marking the beginning of this vernal window. So you're lengthening it by having earlier snowmelt. What about canopy closure? Well, they have data for that too. They've been very, very robust in their data collection. And we can see that canopy closure has typically been occurring somewhere between May 28th and May 21st. So that too has been advancing, but not at the same rate. This is only occurring 7 days earlier. What that means overall is that the vernal window itself has lengthened by about 8 days. This is 8 more days of kind of muddish season. Anyone here favorite season, mud season? No. Oh, you like mud? No. Yeah, mud season. Yeah, not my favorite. It's certainly not one that I look forward to lengthening. And ecosystems as well don't look forward to having this lengthen. When you look at a longer vernal window, this means that there's going to be phenological mismatches, not just in terms of carbon, energy, and water, but also in terms of organisms. When birds arrive earlier than their food sources become available. When you have the delivery of nutrients into the Gulf of Maine, yet there aren't any critters there to take advantage of that delivery. There's a lot of uncertainty associated with this. How fast is it going to happen? Can we track it? Are ecosystems and critters going to be able to adapt fast enough to accommodate this change? And the ones that can't, who are they? What role do they play in sustaining our ecosystems? These are a lot of questions that need to be answered and researchers are working on very hard. I'm going to talk a little bit more about the energy, carbon, and water-related ecosystem processes. The first one is my favorite, albedo. Has anyone heard that word before? Yeah, nice, excellent. So albedo, it's a measure of reflectivity. If you think about what you wear when you go out on a hot summer day, if you wear a white t-shirt, you're generally going to stay cool. If you're wearing all dark clothing, you're going to be absorbing a lot more of the sun's energy and you warm up. And this fundamental process happens on local to regional scales. This is a photo of my field site. One photo taken in the middle of winter when we have a very snow-covered landscape. It's like draping a white t-shirt over it. And another one, also in midwinter, but we had no snow that day. It's a fundamentally darker landscape, and that means that it is absorbing a lot more of the sun's energy. The soil is not as likely to be frozen, especially when it's in an open environment like this. If it's shaded by a canopy, might be a little bit more insulated. But when you remove that snowpack, it enhances and accelerates winter warming. And this is probably one of the reasons why, historically, we've seen winter warming at a faster rate than other seasons. We can also look at that change in carbon cycling. This is what I had mentioned earlier. During a snow-free period in the middle of winter, if that starts up and you have an abundant amount of sunlight coming into the forest floor, those warm, dark soils are going to absorb that solar radiation and warm up. The microbes are going to start respiring. This is the basic equation that my students have to remember for their exam next Wednesday. And essentially what you need to know is that respiration, decomposition, releases CO2 from the ecosystem. Later on, when the canopy does finally leaf out, it will start taking up CO2. But we're looking at a lengthening of that time when CO2 is being released. So a major research question that we're trying to answer is, do the ecosystems make up for this in the growing season? And right now it's not quite clear. So it's something we're looking at. When we think about water, the period between snowmelt and peak streamflow is also very critical. We've had recent years, however, when instead of just have baseline flow, and then the spring freshet when you have a peak in stream flow and then it returns to base flow, that's kind of been happening in a much more pulsy sort of pattern. So you'll have base flow and a melt, base flow and a melt, right? You guys remember the February 2017 and 2018 when it got to 70 to 80 degrees? That's the type of pattern that we're starting to see. And this too could be influenced by frozen soils. Imagine if you have a winter with very little snow cover, but it remains cold. Those soils can freeze, and now if you have rain in the middle of winter, your frozen soils are going to act like an impervious surface. So what happens to all the nutrients that are sitting on the surface? They're going to get washed into our streams. And whereas before we might have seen a snowpack absorb that, now we're going to start seeing a delivery of nutrients that is very unexpected into our ecosystems. So what will the vernal window look like in the future? This is a photo I took from one of my field sites, and it was mid-February. Well, I guess it was more like late February. This was February 26, 2017. This was also the warmest February day ever recorded in Boston. People were walking around in shorts and t-shirts. People were doing yoga on the docks. So this isn't just like an impact on our ecosystems. We also see a fundamental impact on our economy. In northern New Hampshire, 45% of the visitor spending in our northern rural counties comes from the ski industry. And when they see a winter like this, people are not as motivated from the Boston area to make the trek up to New England, northern New England, I should say. They're much more likely to go out for a bike ride and not come up to New Hampshire and buy a lift ticket and spend money at a restaurant. So we see about a 30% decrease in skier visitation during these winters. And that has a hard time on our economy as well. To get into precipitation, this is a trend that we've seen. Northeast US is a very big hotspot for increases in extreme downpours. A lot of this is due to tropical cyclones and hurricane tracking storms, also a little bit from winter storms coming into the region. But compared to the rest of the US, 71% increase in their heaviest 1% of daily events over the period 1958 to 2012 is not something that should be ignored. If you think it's been getting rainier, we have data to back that up. In the future, however, this is looking at just summer precipitation, we actually don't see much of an increase. Sure, it may be becoming more pulsy and becoming in more larger events that are farther and further between, but overall we're not seeing a big increase in summer precipitation. When you have warmer temperatures, but keep precipitation the same, that means that you're increasing evaporative demand. That means that our ecosystems are more prone to drought. You need to have a commensurate increase in precipitation to match a warmer temperature if you want to continue to see the type of summers that we've had. Summer 2016 wasn't a good example of this, right? I remember driving back from Colorado and we drove through upstate New York and I saw wilty oak trees. That is not something you see very often in this region. In wintertime, we can expect to see increases in precipitation, but we also know, again, that temperatures are going to be warmer. This means that we're going to get more midwinter rain, and more likely we're going to see rain on snow events. Those too have an impact on hydrology. When it comes to sea level rise, this was just a map I picked up from the NOAA Sea Level Rise viewer. This is showing the mean higher high water, right? So we can see our lovely salt marshes there. We're somewhere around, this is the Parker National Wildlife Refuge. I think we're somewhere up there-ish, yeah. These are the areas that have been marked as vulnerable. So anywhere that's in that light color red, those are medium vulnerability, meaning they should keep an eye on it. Anywhere that's in red, that is very high vulnerability. They're probably lower in elevation or just not accommodating for the fact that they will have higher waters in the future. Under a 1-foot sea level rise scenario, you can see a lot of these salt marshes will likely be inundated. And that could be problematic for the ecosystem as well. Currently, they probably get inundated during their king tide flooding events, right, the highest high tide of the year. But if this is happening much more frequently, we could start seeing some fundamental shifts in salt marsh ecosystems. So to wrap up, this is probably, actually, I'm wrapping up really early. I'm so sorry. Yikes. The solutions, we need to mitigate and we need to adapt, right? This climate change is pretty much an innovation opportunity for the 21st century. If we think about prices on carbon, promoting energy efficiency and renewables, conserving ecosystems and key carbon sinks, right? Our forest ecosystems are huge here, and making sure that they retain that carbon into the future is going to be very important. Transitioning to lower carbon food systems and then adapting to unavoidable climate change. At a certain point, you have to accept what's coming down the pipeline. For me, a lot of this comes down to not just the impacts on ecosystems, but also on our psychology. And it's not one that's talked about a lot in the climate world, but it's something that someone who's plotting up data every single day experiences firsthand. When I see something like a snow plot that's saying that I'm going to see about a month of snow or less in the future, it has an impact on me. Have you guys ever heard of the word solastalgia? It's a combination of the word solace, right, the comfort you get from being at home, and nostalgia, that sort of memory that's tied to that. And when you think about the environmental impacts of events like climate change, that feeling you get in midwinter when it's 80 degrees and it just doesn't feel right, right? The leaves aren't leaved out like they normally are when it's 80 degrees. That can have an impact on you. And for me, it just feels wrong. I look outside and I say, this isn't the way my home used to be. I also think, boy, I really wish it was snowy outside. It would be so much easier to have the Christmas tree up and be looking outside at snow. It's a sort of impact that doesn't get documented as much as it should. But it has been applied to mountaintop mining communities, right? Folks grow up with a mountain in their backyard and a coal mining company comes along and chops the top off. That has a huge impact on your psychology. The mountain you grew up with, that your grandparents grew up with, is gone. And we can see that with climate change. It may not be a huge mountain that's missing in our ecosystems, but it could be something as fundamental as snow. It could be something as fundamental as the salt marshes that we look out over here. With that, sorry to be a Debbie Downer, I also like to think about the hope for the future. So one of the things I do and I contribute in my world is to educate. And you all have shown up here. You have shown your dedication to education, and I appreciate that. And you also have your dedication to solutions. And to me, that's what matters the most, is working together, not just on the global scale. We know that certain countries have not adopted the Paris Agreement, or they've stepped back from it. And that says something. It says to me that we need to step up on the local level, and you're all here doing that. So with that, I'd like to conclude, and I'm looking forward to hearing a lot more about the solutions you guys are coming up with. So thank you. So I suppose since I've ended early, I have plenty of time for questions. Yes?
This is excellent.
Okay.
Always like time for questions.
Yeah.
I'm sure no one has any.
No one at all, no. Gotta go. Oh, yeah.
I don't have to have one.
Okay.
Please do. I have a concern about all the carbon that is trapped up in the permafrost and stuff at the higher latitudes. How do you incorporate that in your model relative to CO2 and that?
Yes, so that is incorporated into the model. And some models do it really well. Let me just...
Just a parameter, or is it?
Oh, no, a lot of these models are process-based models. So they are fundamentally saying, this is what is happening to the rate of decomposition in microbial communities, and they're based on different studies. Some end up being concentrated much more in what's happening, say, in the North Slope of Alaska, because we have a lot of data there. You might not have as much data from Siberia to capture what's happening there. But it is one of those things that gets captured in the models, and you can see the differences on the global impact on temperature change or precipitation change. Actually, I'm going to go back to temperature so I can illustrate what I mean. Go back up a little bit. Oop, there we go. Right, so noting that there's a range of responses here. A model down here might not have a strong enhancing, accelerating effect of permafrost in it. A model that's way up, where did my memory go again? There you go. A model that's up here probably has a very strong feedback. And these feedbacks are not just permafrost, it's also the albedo feedback, so the loss of sea ice also accelerates warming through that albedo effect, right? You remove a bunch of reflective sea ice and expose darker ocean, you're gonna start seeing an acceleration of warming in the Arctic.
So I feel better about the fact that you have an interactive model.
Yes, yeah, no, these are these are highly dynamic and interactive models. The atmospheres are communicating with the land surface and the ocean and moving a lot of different materials through these systems and energy and water, yeah. Sorry.
You mentioned the Paris Accords, something that I don't know much about yet, and CO emissions. Just from a lay person's point of view, if China and India or Mexico, countries contribute huge amounts of emissions, no matter what we do, doesn't that seem insignificant? And how did the Accords address that issue?
The Accord is non-binding at this point. It doesn't have much teeth. However, the countries that do adopt renewables in the future, they're going to be poised for a much more efficient economy. It costs money to extract fossil fuels. There's no doubt about that. And coal usage is on the decline in the US. I think we're at like the lowest levels in 39 years. To point the finger at someone else and be like, well, they're doing it too, I don't think that's a good excuse for inaction. I think it means that you need to work much harder to ensure that your future is adopting for this change, and that you need to make sure that you're doing your part. I have a 4-year-old, and so I also like to think a lot about Horton Hears a Who, right? There's no shirkers in 12J. So remember that line? Yeah. So, I mean, this is something that like everyone's got to step up in any way you can. You can't be the shirker in 12J saying, well, everyone else is doing something, I don't need to do anything. That's my opinion. Yeah. Yes?
Trying to translate this general climate science to what's the impact on the quality of water on the Merrimack River. Clearly, warming atmosphere and warming earth will create warmer river water.
Yes.
Setting that aside, what else is happening to the Merrimack River? It seems to me that the increasing frequency of storms will impact the frequency of sewage overflows into the river, as well as increasing the amount of stormwater runoff that puts pollution into the river. Have you looked at that at all?
It's not my area of research, but there are other researchers at University of New Hampshire and many other universities in the Northeast that are looking at that. Specifically at UNH, the Water Systems Analysis Group looks at stream temperature. And they're very concerned, again, about that vernal window period. When you have headwater streams that typically would have an earlier canopy, right, that covers it and shades it. If you have a longer period of time when those streams are exposed to sunlight, that means warmer stream temperatures, not just downriver, but at the headwaters themselves. And that too has a fundamental impact on the ecosystem because you're looking at something that's no longer hospitable to organisms that thrive in those cooler headwater streams. I don't know the details about how that propagates down the ecosystem, but ultimately it can lead to more runoff of nutrients because organisms aren't taking them up there. And when you mentioned sewage effluent, my husband actually, he was going to kill me for telling you this, he used to work at the Durham wastewater treatment facility, and he would test the water as it's coming out. And you would have these periods of time when, in UNH at least, right, the students leave, and all of a sudden things drop to near zero. Right? There's not as much waste input there. And if you think about the change in population just in general in the northeastern United States, some folks are very concerned about the growth of the population here because in terms of the grand scheme of things, we're poised to be resilient. We're not looking at forest fires. We're not looking at extended long-term drought. Short-term drought, sure. But long-term drought, like what they see in the Southwest, not as much. Extreme precipitation, nuisance flooding, absolutely. But compared to the devastating floods that you see in places like Hawaii, they got 3 feet of rain in 24 hours. And we're complaining about 4 inches in 24 hours? Like that is a completely different ballgame in what they're dealing with. But to address your question about sewage effluent, like that certainly speaks to capacity. What can we expect for population trajectory into the future? And I think that's going to be a major driver in addition to land cover change. Yeah. I can't off the top of my head, no. I know Durham, New Hampshire is putting in a new one right now. I don't know how state-of-the-art it is. You're nodding your head, so maybe you know something about it. Okay. I think it's including tertiary treatment, so really addressing more nitrogen-based loading. That's certainly an issue that we are confronting in the Great Bay. Sherry, she is here. Yeah, do you know about the Durham treatment plant at all, or what they've been doing?
I don't specifically know about Durham's actions, but I know in general, I'm with the Department of Environmental Services in New Hampshire, and there's a lot of work going on within our wastewater engineering bureau to make treatment plants more efficient. Because if you think of where a treatment plant is located, it's located at a receiving body, right? Because they have to dump somewhere, so it's either on a river or some lake. And so not only are they big energy users, but they're also very vulnerable. And so our agency is very aware that this sector needs a lot of attention, and we applied for and received a Department of Energy grant to work with the wastewater treatment facilities in our state to be more efficient, because they also use a ton of energy to treat the water. So that's a great thing that they're doing. And then we're also looking at asset management. So having wastewater treatment facilities understand the assets that they have, their pumping systems, their lift stations, all the pieces that they have, and where are they located? Are they in floodplains? Are they vulnerable? And what can we do to make them less vulnerable? So while it's not specifically looking at effluent condition, it's setting up all the parameters that would provide us a better effluent condition, because we're looking at our flows, how we're going to manage them. As Dr. Burakowski says, we may have an influx of people from the areas that are uninhabitable because they're going to come here because we have water. So how do you plan for that increased capacity as well as having a good quality effluent?
Perfect. Thank you so much, Sherry. Sorry to put you on the spot. I knew you'd have a better answer than me. Yeah.
Is anybody researching sort of global scale reactions of what the climate is going to do? Are there going to be feedbacks? For instance, if we have more, if we have higher sea levels, that's going to be a bigger surface water or surface level water.
Mm-hmm.
Is that more reflective than land? So is there going to be some sort of negative impact at all? Is anybody looking at anything like that?
Yes, so there are a number of scientists that focus specifically on feedbacks and which direction the feedback goes. Is it an accelerating feedback? Is it a dampening feedback? And for some of the feedbacks, they can have two different answers that are of opposite sign and magnitude. And that's what leads to these uncertainties here. And understanding especially where those negative feedbacks are, because those are the ones we really want to latch onto and say, like, we have to leverage this. Anything that can dampen the response is something that's being investigated. There's a wide variety of them, like carbon. As carbon increases in the atmosphere, a lot of folks are interested in how plants respond and how much carbon they take up. They generally require more nutrients in order to take up more carbon, but again, where are those nutrients coming from? But yes, absolutely, people study it for sure. Yeah.
I just want to throw on to this discussion of the increased risk of effluent from sewage treatment plants, the increased risk from toxic fuel storage sites, from increased flooding. And that's something that people can do on the local level by working with their local emergency responders, not just to focus on responding, but on prevention.
Yes.
They go out and inspect these sites ahead of time, and make sure they're hardened against increased flooding. A lot can be done.
So my spouse also works on, now he works on Superfund sites. So he's gone from one glamorous job to the next. And in that one, they're actually in the Passaic River right now, and they're looking at what happens when you have a really high impact flooding event. What happens to the sediments? Because that is one of the nastiest bodies of water that we have in the US. It's everything that you don't want to see in water. Mercury, lead, PFAS, it goes on and on, yeah. And then way in the back, yep.
If I like skiing at places like Mount Sunapee, and I look at your chart there, it looks like by 2050, I'm going to have to go further north. Am I reading that right?
I will say that ski resorts have been amazing at adapting to a changing climate. They can make more snow in a shorter amount of time and cover more acreage, like orders of magnitude more than what they could do in even the 90s. And in that sense, they're very resilient. And so to say, I wouldn't say that Sunapee is going to be closed in 2050. Are they going to have to invest more in adaptation strategies? Absolutely. Will the resorts at higher elevations and more northerly locations be more and poised in a better position? Absolutely. And especially in Colorado. So this is actually an interesting case study, not just in adaptation, but in mitigation. The resorts that are much more resilient to climate change, the Aspens, the Vales, the ones that have a lot of money, that are at high elevations, that get a lot of snow, they're the ones that can speak. They're the ones that can lobby, and they are. And that to me is encouraging. So Aspen specifically has what's called the Give a Flake campaign. They've been putting postcards in ski magazines and saying with a message, short message to your senator or representative, this is important to me. I want you to do something about climate change. You're not doing enough, that basic message. Postage paid, send it in the mail. And for them, that was a big risky move, because their clientele runs the political spectrum. If anything, they might lean a little bit further to the right, which historically has shown to be quite partisan when it comes to climate change opinion and solutions. So for them to make that move, and with the hope of getting a first follower response, right, getting other resorts on board, that to me is encouraging, and that's an important role that they can play. Yeah. Yep.
Specifically what's been effective that you found most effective?
Absolutely. So I've been running a citizen science program out of the University of New Hampshire that has local high schools and middle schools involved as well, and we measure albedo. It's a relatively low-cost instrumentation. I'm working on making it even lower cost, essentially taking the image sensor on your cell phone. This is like my grand career plan, is to be able to point the image sensor to the sky, measure what's coming in, flip it over, measure what's coming out, and divide the two images to get albedo. It's been historically a little difficult because their camera is not silicon diode receptors. It's a sciencey thing that you have to convert it to an energy output. And for them, it's become a really easy way for them to measure their own environment. They do this right in their backyard. Usually on the ball fields is a great place because it's wide, it's open, it's flat. They get a lot of snow. They're not shaded by canopies. They also measure snow depth and density. So most of you can probably feel the difference in snow, right? Fresh snow, you pick it up and it's very light and fluffy. That stuff's really good insulator. So you can also measure soil frost depth with some relatively low-cost instruments from Home Depot. Costs about $25 to make one of these. I should have brought one. They're really fun. And they're easy because you get to like pound them into the soil. But you essentially put PVC tubing into the soil, and we did this at 5 schools recently. And it has a special chemical in it called methylene blue. It's non-toxic, but generally like you don't want to drink it. And it has a special property where when it freezes, the methylene blue gets excluded from the ice. So you see like a little ice cube in your tube, and you know that that's how deep the soil froze. So they can actually track that with their snow depth and density measurements and keep track of how that's going to change over time, because we're really not certain how stuff like soil type impacts soil freezing. And if we're looking at, soils being frozen and acting as an impervious surface, that's information I'd like to know and be able to pass on to a hydrologist. So I spent quite a bit of time in schools and give them tools and instruments to work on that. So the soil frost data we upload to the GLOBE database. This is Global Learning and Observations to Benefit the Environment. This is funded by NSF, NOAA, NASA, a variety of different federal agencies fund it, and then it's run out of the Department of State. So it's an international program, which has its benefits because it means that I can compare my data in New Hampshire to, say, a school in Sweden, who also experiences seasonal snow cover, but has completely different soils, right? Yes?
Your love of skiing is apparent, and if you have some place like a Vail, an Aspen, you commented that they can fix it. They've got a bank account that can afford to go at a process that a mom and pop place would probably go out of business.
Mm-hmm.
I personally like skiing at mom and pop places that have an attraction. So it seems like the economics really are community in it. You can't use the same model general. There's no general economic model. So I live in Newberry, and I would really have hurt. I'd feel hurt if I couldn't use my waste treatment plant for a month. Let's say it's gone because of some circumstances. So, but I believe that here there could be the economics to sort of look at that and say, well, we might be an asset. So how can that individual feel the pain? Well, I'm personally thinking about gas costs. When that goes up, I don't travel as much. But if my water bill is a certain level, I say, well, that's a lot of money going out. Why? But how do we get the pain? I think getting the pain to the individual is not an education. I personally think it's a pocketbook.
Is it what, sorry?
I think it's more of the pocketbook.
The pocketbook, okay.
It's going to cost me a lot to open up my spigot and run water down the drain. So I'm going to charge less. But that's simplifying it. The economics in my community, there's a lot to take care of in order to keep it precious. So tourism is peaking out and growing, because what would we do without people wanting to come see and visit?
Yeah, so maybe I haven't communicated the role of the Aspens and the Vales correctly. Their job is to lobby to their representatives. So for example, it's the 6th district in Colorado is Scott Tipton. He's on the Climate Caucus. He's also on the Ski and Snowboard Caucus, little known caucus in the House. But I went to the Ski and Snowboard Caucus because Annie Custer of New Hampshire is also on that caucus. And I look at their website, there is zero mention of climate change on that website. Aspen's role is to make their representative do something. He's the Republican. He needs to take action. And if he's not going to, Aspen's going to be working very hard to get him out of office. Because when you think about a place like Colorado, iconically, do you think about skiing? Probably. They're the #1 ski state in the US. They have like millions more skier visitations than we do. They also have a lot of fracking. Do they want to be known for their skiing or for their fracking? And right now, Scott Tipton is much more playing to the hand of the fracking industry. And that's the role that Aspen can play, is swaying public opinion, of swaying the way that these people are voting in Congress. So it's not so much of like, hey, can you just save us? you know, we're hurt during bad snow years. This is much for a broader impact across multiple facets of society. So I hope does that make sense? And I think it's a really gutsy move on their part to be doing that. Yeah.
I think one of the challenges is that the change that we've had so far has made our weather more temperate. So we're seeing the benefits of warm winters, and unfortunately, many people like that. I hate that because I'm a cross-country skier, so I don't like that I don't have snow, but I don't know anybody else who does that kind of activity. So if you don't have a connection like you have to skiing, how do you convince people that warmer winters are bad when it's just a matter of time before we get the summer effects that haven't really, like you showed, they haven't really kicked in yet?
Right.
How do you bring those present?
It is absolutely much more difficult to connect with a community that's just like, yeah, well, I kind of liked winter 2016. My plowing bill went down, my heating bill went down, I didn't have to shovel, I could go biking. Like, it is hard to reach that community. And you're absolutely right. The way to reach them is trying to identify their shared values. What do you have in common with them? And what is the impact they're going to see from climate change? Maybe they're hunters. Maybe they're going to start seeing impact on moose, right? They like hunting moose, and if they're going to start, we've already seen the impact on moose. I mean, winter ticks are no joke, right? That's linked to winter. So to try, it takes effort, and sometimes, you know what, you don't have that connection, but you find someone who does, and that's essentially where it needs to come from. Yeah, you can't convince them with facts. Yeah. Many hands. I haven't heard. Yeah, already heard. Did you have a question already? Yeah. Okay. So why don't we move? Someone else ask a question first. Yeah.
Yeah, I'm curious about impacts of the Vernal Window on Streamflow. Thinking about tributaries. That we think of that window as the time when you get recharge of groundwater.
Yes.
It's the only time, and then the corollary in the fall. So, well, maybe that's maybe a positive thing, or do you include that in what you're looking at in terms of impacts on rivers and streams?
So I personally don't, but my colleague Danielle Grogren does. She's the hydrologist in our research project on that realm. I'm more the snow scientist, and then we have the soil biogeochemist, and then Danielle covers the hydrology. And the model that she works with, it's the UNH water balance model, has groundwater aquifer representation in it. So that's going to be one of our research questions, is what does this impact? What is the impact of low snow cover years on groundwater recharge? Can we make up for it with more extreme precipitation events, or precipitation being distributed throughout the year? It's an unanswered question that we're definitely interested in. It's an important one. We don't do too much irrigation here, but we are, you know, we can't say, oh, it's gone. You know, we don't want it to happen that way. We'd rather keep an eye on that ball. What's that? And a lot of private drinking wells, yeah, definitely. Way in the back, yeah.
What model resolutions reflect feedback and portions most accurately, or do they all equally?
When it depends on the scale, obviously. So for something that's happening in mountains, like albedo feedbacks, higher resolution certainly tends to do a lot better. If you have like 110 kilometers large mountain, that's not very representative of what happens in the mountain environment. So there are some models that certainly scale down to a much finer resolution. I'm not 100% sure on permafrost feedbacks, but knowing a lot more about how much carbon is in there, it's very spatially heterogeneous. Right? You can measure carbon permafrost over there, and then like a couple miles down the road, it's going to have a different carbon content. And that can affect your results. So accounting for those uncertainties is something they can do. It doesn't necessarily mean that they can represent it well in their 110 kilometer models, but they do the best they can, yeah.
Just a real quick request to you and Rusty. I really like the idea of your citizen science experiments, and maybe you could work with him to give us a link.
Absolutely, yeah. Yeah, it's on, I have it on my website, and it's relatively fun to put them together. And we're putting our recipes together so they're easy to follow and give you an Amazon or Home Depot shopping list so you get exactly the right materials on there. Yeah.
We'll supply the citizens, you supply the science.
I can do that, yeah.
I had a question. I hope this isn't impertinent. It's sort of one of these nasty policy questions. Oh, by the way, we are looking for a microphone to circulate in the audience, and if we can find it, we'll use it. If we can't, just everyone speak up so we can all hear. What, in terms of policy, just sort of your unscientific take is, what are some of the things that we in the Merrimack could do best working together to approach climate change? I mean, you know, given its limited resources, what makes sense now for us to collaborate on and work together on?
Again, I'm not a policy expert, so thank you for acknowledging that, because I definitely am not. I'm a scientist first, and I try and keep track of policy. One thing that's really bothered me in New Hampshire is the lack of incentivization for solar. And to me, that's just not forward-thinking at all. It's very myopic. Our leadership's commitment to fossil fuels is frustrating. New Hampshire has no fossil fuel reserves. This does not benefit the state of New Hampshire to have that. And for me, that seems like a no-brainer. Let's subsidize this. Let's make it easy for people to access solar resources and other renewable energy resources. Why wouldn't you? It just makes sense to me. Yeah.
It's interesting because I think Massachusetts is kind of the contrary example that probably has the second highest use of solar next to New Jersey.
Yeah, we're last in New England, and that's embarrassing for New Hampshire. Yeah.
First of all, in New Hampshire, I'd say don't lose faith because your whole management just changed.
Yes.
But my question regarding the river and its tributaries would be, as I observe it as a conservation commissioner, it seems that where the river is, notwithstanding all the other legitimate problems, is really taking the hit as a death by 1,000 cuts in its tributaries. And I think, I don't know, I don't have the science available, that it's a result of runoff, and I think it seems to me intuitively that it's a result of, you know, I mean, you could call it spring, but it's not. We no longer have springs like we used to have. We have a second winter, and it seems to me that that's where we're really on the ground seeing the damage and the need for protection. And it concerns me about things like nutrient loading might be one example. Have you speak to that at all, about the risk of the tributaries and
so mentioning that change in hydrology that you're noting at, we're also seeing changes in fall hydrology. So I don't know if you guys knew this, but up near Hubbard Brook, Mirror Lake was ice in on the earliest date ever, November 20, I think it was 24th or 26th, and then it iced out again. And that had never happened in the history of record keeping at Mirror Lake. So you can imagine that streams probably had similar responses, right? We had a very deep snowpack. It was very frozen. It was very cold, unseasonably cold. And then you had a shift back to more normal conditions. And I think that's going to be the name of the game moving forward, is that we're going to have these highly variable winters with the midwinter melt. That becomes much more, it's beyond the regular January thaw that we normally see, but into like 60, 70, 80 degrees sort of warming events. And I'm not sure exactly what those impacts are going to be. Again, this is why I have hydrologists on my team working with me. But certainly folks are definitely looking at that. And there's a certain intersection that happens as well with land cover change. A lot of the land in New Hampshire that's forested is privately held. And you don't have as much impact on how they manage their land if it's privately held. What impact does that have on hydrology as well? I mean, we know in the 1800s when you deforested the landscape, that really increased runoff. And that was a big impact. Are we going to see that again in the future? It's a good question. And those trees are definitely getting older. They're becoming more harvestable and valuable. I think that probably is something we should keep an eye on, and definitely something that needs to be included in models. And there are people at UNH who do that in the Water Systems Analysis Group. But in terms of the actual physical, biological impacts, that's not necessarily my area of research, but it's definitely something folks are keeping an eye on. Yeah. Yep.
We have maybe one more question. Is that?
Sure.
I do a lot of restoration work on the salt marshes out here, and in the face of sea level rise, we look at innovative ways to try to help the marsh keep up with sea level rise. And I sometimes get pushback from regulators on you're making a value judgment that you want to try to keep a high salt marsh versus what it's turning into a low salt marsh. And how do you decide what's better? And I'm just wondering if, it's not that you were specific with what you can do with this type of climate change here, but do you get that kind of pushback where New Hampshire will now become a
Mm.
later through the questions that I get.
I think one thing to highlight is just the pace.
Yeah.
We have had transitions on glacial scales before, you know, as glaciers retreat, as sea level rises, salt marshes do form over thousands of years. And the transitions aren't necessarily as rapid as what we're seeing today. And having that type of uncertainty to me is enough to track the problem and take action where necessary.
There is adaptation that is going to occur.
Yeah.
So it's like, how do you, why are you choosing this versus that?
Mhm.
That's what I'm often getting at. It's a tough one, yes, the pace is obviously it. The economic cost and the inconvenience and all that is an issue, but on the environmental level, it's like, I don't know how to answer it.
Yeah. I mean, sometimes you don't end up with a good answer. Again, like I have a hard time answering to the people I like, but I like a lower heating bill.
Yeah.
I can't answer to that. It's hard, you know. Okay.
Well, thank you, Dr. Burakowski.
Yeah, thank you, everyone.
We're going to present you, Dr. Burakowski, with one of Ellen and Kenny's fabulous calendars.
Yeah, well, that's definitely going to go in my office. I'm glad I ended early. That was a wonderful discussion, and thank you all for your wonderful questions. That's great.
I don't know if you